We could replay that.
All right, well, welcome everybody to Understanding the 2015 Michigan Residential Energy Code. This course in its entirety is approved for 3 hours of continuing education units. Each individual session is approved for one. GBCI, AIA, AIBD, Certified Green Professional, NARI Green, and is applicable to the Michigan Builder's License and continuing competency in the Green session. Today I'm your moderator. I'm the Executive Director at the Green Home Institute. We're a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. And a huge thanks to all of our supporters who allow us to do what we do: Anderson Windows, Panasonic, Build Equinox, Sun Intuitive, all of our members, sponsors, board of directors, and volunteers. All right, so with that, third and final session here is going to be doing a big focus on the biggest change to the Michigan Code, and that is the ventilation section of that. And we're really excited to have Jeff Palinowski from Panasonic to be joining us out of Wisconsin today to talk about ventilation strategies, unique opportunities, and what it means to meet this new code. So with that, Jeff, take it away.
Very good. Can you hear me well?
Yes.
All right, very good. So good morning, everyone. As Brett said, my name is Jeff Klanowski. I'm broadcasting live today from beautiful Green Bay, Wisconsin, where our Packers are dwelling near the middle or the bottom of the NFC, and the Lions are, of course, leading the pack this year. So congrats on that. A little bit about my background. I've been involved with ventilation in the residential building market, whether it be single or multifamily, for going on about 20 years now. Have gotten a lot of education from builders over the years on how things work, and other code officials on how things need to be interpreted. So that's a little bit about my background. I come out of the utility program industry, running energy efficiency programs, and that includes air sealing buildings and that type of stuff. So I've spent more time than I'd like to crawling through fiberglass insulation and whatnot. But this presentation I'm going to do today is a truncated version of a longer introduction to ventilation presentation that I do to HBAs, and architect firms across the country. What I would like to do today is focused specifically on the Michigan Code as much as possible. And the things we want to cover today are understanding the necessity for ventilation, understanding the differences between whole house, intermittent, and spot ventilation, and then evaluate the differences of exhaust, supply, and balanced ventilation options. And we're going to talk there a little bit about the costs, and then we're going to move on to sizing a system. The sizing system, I'll kind of go through, sizing the ventilation system, I'll go through pretty quick, because in Michigan you've got just a nice, easy way to do it. You look at a chart, look at the number of bedrooms and the square footage of the home, and just work with that to come up with the amount of ventilation that you need. But I want to give a little background as to where those numbers come from. And then finally, and certainly not least important, is understanding some fundamentals of installing ventilation systems properly, because you can buy the best ventilation equipment in the world, but as you know, like anything, if it's poorly installed, it's not going to perform the way you wanted it to. So those are the things I'd like to go over in the next 30 minutes. And when we get done, we'll do a quick review, make sure I've covered everything. If you have any questions, go ahead and type them in as we go along. Brett will try to capture those and bring up the ones that we feel are necessary to address right away, and other ones we'll probably hold off until the end. So first, let's talk about why we need to ventilate. As you know, homes are getting tighter and tighter. And as much as it is for building codes, it's also for the occupant's comfort level. And that's probably that as much as anything, that, people are not going to accept a home anymore where they're feeling cold drafts blowing through outlets or around windows and doors and that kind of stuff. Our homes have gotten much tighter and tighter over the years, and that's created an indoor air quality situation that, has to be addressed. And, we got to keep that indoor environment healthy for the occupants as well as for the building. You've got a big investment there in the home, and if we don't manage the moisture and the pollutants properly, it's going to damage the home, but it can also not only reduce the occupant's productivity and overall health, it can lead to some pretty serious health risks. So we have to, now we have to introduce mechanical ventilation. Didn't used to be necessary because houses were leaky enough that there was enough fresh air flowing through them, but with the building envelope getting tighter and tighter, we need to do something mechanically to introduce fresh air and remove the pollutants. And let's talk a little bit about what's changed with homes over the past 15 years. We've along with the introduction of the blower door test and HERS scores and all of that, homes have gotten tighter and tighter and tighter, and the mechanical systems have changed as well. So when we look at the building envelope, one of the things that has certainly changed is the amount of insulation that's required in a home, as well as the type of insulation. 30 years ago, we used zero foams, whether it be a closed cell foam in the walls or on the rim joist to seal up that rim joist and stop that, leakage there, or on the attic floor, or foaming around the windows and doors. We use foam now, and that has contributed significantly to reducing the leakage, increasing the comfort, but also trapping those VOCs that are off-gassing from the building materials that we use, trapping that moisture that comes out of the foundation after it's poured. There's a ton of water there, and the first year or so after, all of that moisture is working its way into the building, and it has to be exhausted. So certainly by code, our envelopes are tighter, and therefore, we need to do something to improve the air quality for the occupants. And in terms of mechanical systems, if we have any HVAC folks on the line, they'll know the answer to this question. 20 years ago, where did the combustion air come from for the furnace? Oftentimes it came, I should say oftentimes, 20 years ago, it came from within the home, right? It got sucked into the furnace in the basement or the mechanical room, went through the combustion chamber and out the chimney. Well, nowadays, the combustion air comes in through a plastic tube. It goes into the combustion chamber, through a couple of heat exchangers, and back outdoors to exhaust those combustion gases. So even that mechanical ventilation, if you will, the furnace drawing air out of the home and exhausting it through the stack, that was mechanical ventilation, and we've lost that as we've increased the efficiency of our furnaces. So, not only have our buildings gotten tighter, we've actually reduced the amount of ventilation, because in those old leaky houses, the furnace ran a lot, so there was a lot of air being pushed out of the building and thus brought in through the structure to improve the air quality. So we've done two things to really reduce the amount of airflow through that home. And while it's good that we've made homes more airtight, more comfortable, and our furnaces are more efficient, we do need to give a little bit of that back, because we've certainly saved a lot of energy compared to 20 years ago by doing those improvements. But we need to give a little bit of that back to mechanical ventilation and making sure that the air inside is healthy for the building and the occupants. In multifamily situations, it can be even worse, because on a single family home, the exterior walls are all exposed to the outdoors and opportunities for fresh air to move into the building, especially on a windy day. You'll note that there's a lot more air leaking through the building than there is on a calm day. But in multifamily situations, because the exterior of one unit is often the exterior of another unit, instead of fresh air leaking in through the leaks between, in the exterior walls, there's air from another unit or a hallway or, as this picture depicts, even, through a garage leaking up into the floor of the unit above it. So in a multifamily situation, it can be even worse because we don't have that exposure of the exterior walls to fresh air. And equally important, most multifamily properties are built on a tighter budget than a custom home, for example. So oftentimes the components that are going into a multifamily property have more off-gassing than maybe a single-family custom home might be. So those are some of the reasons, that we need to ventilate. So hopefully I've made my case there, and we will move on to, we'll talk a little bit about the ASHRAE code here. Now, in your Michigan code book, you're never going to see a reference to ASHRAE, but understand that most of the building codes throughout the country do refer to ASHRAE. And ASHRAE is the American Society of Heating, Refrigeration, Air Conditioning Engineers. So that's a group that puts together what they feel are the necessities for ventilation, and then that is often adopted as code. And I will show you later in the presentation here that, in fact, your Michigan code is a chart taken right out of the ASHRAE manual and adopted. And it's a real simple way of doing it, and I like that. But I wanted to give you a little background as to where the codes come from. And you'll note, too, that, some of the biggest building programs in the country also adopt ASHRAE as their ventilation code. They don't create their own ventilation code for Energy Star. They don't create their own ventilation code for Building America. They don't read, years ago, the American Lung Association, Healthy House, and those types of programs will usually adopt some version of ASHRAE as their ventilation code. So it's the same in Michigan. So let's talk a little bit about some of the terminology here. Within the ventilation industry, HVI is the Home Ventilating Institute, and HVI, they're the UL of the ventilation world. You wouldn't put a product on the market that isn't UL tested. If it were a DVD player or a TV or a printer, they're all UL tested, third-party tested. And the same is true in the ventilation world, except it's the Home Ventilating Institute that will test third-party testing and certify the product, and therefore manufacturers refer to the HVI numbers in their marketing most of the time. Now, there's a few exceptions to that rule, where the information being promoted isn't exactly what HVI tested out at, but for the most part, if your product isn't HVI certified, you probably wouldn't put it on the market. So these guys have a lot of input on what goes to market. And also, if you see that a vent fan or ERV, HRV, something like that has a Energy Star logo on it, HVI is the company that tests for the efficacy standards, or tests the equipment that it meets the efficacy standards to be Energy Star labeled. So that's a good indicator, of a piece of ventilation equipment that, is worth a second look maybe, because it's been through third-party testing and certified to meet those standards. So that Energy Star logo can be, help in your buying decisions. Okay. Again, this class is, or this presentation is called Introduction to Ventilation. Some of this information you guys already know. CFMs, cubic feet per minute, you know about zones, the noise level that a bath fan or a piece of ventilation equipment makes. Again, these are tests that HBI does and gives us information so that we can publish that information about our equipment. I always like to use as a reference to zones. If you walk out in the kitchen in the middle of the night when it's quiet and you can hear your Energy Star refrigerator running, that's about 1 zone. And that's kind of the standard for, bathroom ventilation these days is 1 zone or less. So just to kind of give you a reference, that quiet hum that you hear in the middle of the night coming out of your Energy Star refrigerator is about 1 zone. Static pressure is one that maybe some of you aren't quite as familiar with. Static pressure is the resistance to airflow. So again, we talked about at the end here, we're going to talk about, sorry, I had a little interruption there. We're going to talk about installation of ductwork and whatnot, and how that affects the installation and the performance of a piece of ventilation equipment. So we're going to move on to that and how important it is to make sure that we reduce the static pressure as much as possible. Static pressure is measured in inches of water gauge. So when you look at a piece of equipment in a catalog or online, that's how you'll see the CFM performance referenced. You'll see it performance at 0.2 inches of water column or 0.25 inches of water column. Panasonic has all of their product tested at 0.25 because we feel that's a more realistic install. HVI normally does the testing at 0.1 inches of water, of static or water gauge, and we actually feel that that's not a real-world install application, especially since a lot of product is installed with flex duct. We feel that 0.25 is a better test of real-world performance, so we have all of ours tested and published that information there. So the big thing here is to reduce the amount of static pressure to help the fan perform at its optimum level. So here are some pictures of some common install mistakes. I'm sure most of you have probably seen some of these where the takeoff is pointed in the right direction, as we have in that far right picture there. Look at the amount. If every 90-degree turn adds an equivalent of 10, or in the case of flex duct, maybe 15 feet of equivalent length in terms of static pressure, that picture on the far right, we've got 1, 2, 3 90-degree turns before we get a foot away from the fan. So certainly not an optimal install there. And then the picture in the middle, attaching mechanical ventilation requires attaching hard pipe, galvanized pipe, requires some screws to hold that in, and it's not uncommon. On occasion, we'll get a call that, the fan is too noisy, it's not performing right, and they did all the things right. They used hard pipe, they kept it short, not too many elbows, it went right to the outside, and oftentimes it's either a screw that's pinning the damper shut, or they'll forget to take the tape off of the damper before they do the install. So either one of those can be common install problems. And then you've all probably seen, the picture on the left. Yes, we want to ventilate. We went to duct our fans to the outside, and we don't want to have, terminations to the front of the building. So often they get run to the back of the building, but draping them over trusses where they can create pinch points, especially if, you get water weight in there from condensation, can create significant static pressure as well. So we want to do everything we can to minimize, elbows and whatnot, and get rid of that static pressure that really does kill performance of a piece of ventilation equipment. All right, so if we all agree that we have to ventilate and can agree that we want to reduce some static pressure, let's talk about the three different types of ventilation that we can use. We can use exhaust, supply, and balanced ventilation. And let's talk about some of the benefits of each of those. And note, too, that I've got here some cost indicators as to each of these systems. And as we go through each of them, understand that your cost is going to go up as we move from exhaust only to supply to balance. And I'll explain why that is as we go through each one. Exhaust ventilation is, just what you guys have been doing, what most people have been doing for the past 20 years. It's just bathroom fans or kitchen range hoods, taking air from their pollution source and exhausting them to the outside of the building, or in some cases to the attic, which we don't want to be pumping moisture up there either. We want to make sure it gets completely out of the building. So nailing the duct up to your vent on the roof, or throwing it into the soffit and expecting it to make its way to the exterior is not going to work. But that's what we've been doing in a lot of cases over the past 20 years is the exhaust-only approach. We can do the same thing, especially in the South. Supply ventilation is very common, where we're now, instead of taking a fan and pointing it to the outside and exhausting air, now we're actually pressurizing the building or pumping fresh air into the building. That's not as common in the North, and I'll explain why as we get into some of the further slides, but we do use this approach sometimes in what we call a fresh air supply scuttle to the furnace. And oftentimes there's a damper near the exterior of the building separating the warm indoor air from the cold outdoor air that opens when the furnace motor kicks on, and the negative pressure in the cold air side, where the tube from the outside is often piped into the cold air return. There's negative pressure there drawing air to the furnace from the rest of the building, and that negative pressure will suck some air in through that tube connected to the outside and bring fresh air in there. Mix it with the house air, and then distribute that throughout the house. That's supply ventilation, and again, maybe not ideal for a cold climate. Balanced ventilation, and here we're going, you'll note that I have on exhaust, I've got $1 sign. On a supply, I've got $2 signs. But on balanced, I jump all the way up to 4, and that might be a little bit of a underestimation there. Balanced ventilation, we're often talking about HRVs and ERVs, and the cost, especially for a fully ducted system, can be significantly more. But this is a ventilation approach where we're taking equal amounts of air from outside and exchanging it, bringing it into the building, while we're exhausting an equal amount of air. So where exhaust only might create a little bit of negative pressure, and supply might create a little bit of positive pressure, in a balanced system, we're going to be pressure neutral, because we're ideally, in a perfect install, we've got the same amount of air, let's say, 100 CFM exhausting from the building, and 100 CFM being supplied to the building at the same time. So we're not creating any negative or positive pressure with the balanced approach.
And Jeff, can you just reiterate which one is required, or if more, for the Michigan Code?
Sure. I believe that you can use any of these approaches for the Michigan Code. The most cost-effective one, of course, is going to be exhaust only. And you can certainly use exhaust-only ventilation to meet both your whole house and your spot ventilation requirements to meet the Michigan Code. Okay. Mike, if you want to jump in at any point and add comment, that's fine too.
Well, the only thing that I would say is when you talk about cost effectiveness, that's on the upfront cost, but the life cycle cost, that cost effectiveness may switch towards the HRV or ERV.
Okay. All right. again, I think, not to contradict, but if we're hooking that HRV or ERV up to the furnace motor to distribute air throughout the house, there's going to be some long-term operating costs there running the ERV, HRV as well, where a DC motor exhaust fan, might be more cost-effective. But we can have that. We'll have that private debate over a beer sometime, Mike. Okay.
and Jeff, I assume you're. Oh, go ahead, Mike.
I wasn't going to comment. I'd have to learn how to drink beer first, since I don't.
Oh, okay. Well,
Jeff, I assume you were going to cover some other strategies to meet balanced without an HRV or ERV. Would that be accurate?
Yeah, I mean, and I could talk about that when we get into that slide. So certainly,
okay,
I'll.
Perfect. Great.
All right. So again, as I mentioned before, this presentation is an AIA certified CEU. So a lot of what I refer to here is ASHRAE. I wanted to have you guys have some background as to where the numbers come from when we talk about the Michigan code, but your code is not going to refer to ASHRAE. But so on the first slide here on the 3 different types of ventilation, we've got the exhaust only strategy. And again, this is a bathroom fan or a kitchen range hood that's exhausting air to the exterior of the building, or in the case of meeting your whole house ventilation requirement, a fan that's running somewhere in the home, either continuously at a low CFM or at a higher CFM on an intermittent basis, so that at the end of the hour you've extracted the number of CFM required to meet your code. And in exhausting air from the building, we have to make up that air, if you will, from somewhere. And that air, to replace what's being exhausted, is leaking through the building shell. So whether it's a leak under the door, or a leak around the attic hatch, or through the mud sill where the foundation and the wood frame meet, the bottom plate, wherever it's leaking in, it's coming in and replacing the air that's being exhausted. And that's actually one of the criticisms of exhaust air, is that we don't know, or of the exhaust ventilation approach, is that we don't know where the makeup air is coming from. But certainly, if it's coming from the outside, it's going to be fresher, and that's the most common place for it to come from, when all of the exterior walls are in fact exposed to the outside. So we're bringing in that fresh air by exhausting air that's either high in moisture or just normal indoor air pollutants, and replacing it with fresh air. This slide here shows, that picture in the bottom right-hand corner shows just that we've got 2 bathroom fans there in the bottom side of the home, ducted straight to the outside. That's a great install, right? Great, straight, hard pipe running right to the outside, minimal static pressure. And of course, on the end of those ducts, we want to have a termination with a lot of free open area, where it's not restricting the flow of air either, because you can put in a really nice fan, do a great job on the ductwork, but if the termination at the end is choking that fan, you're right back to where you started with all the elbows and stuff. Years ago, it wasn't uncommon for fans to be vented to those little silver vents that were in the soffit, which have basically a window screen in them, and they would get plugged and really choke down the fans as well. So we've certainly come a long way since then, and people understand more, about the static pressure, and making sure that we're using a good termination as well. As I mentioned, one of the criticisms of the exhaust-only approach is that, we can't filter that air because it's not coming through a duct like it would with the supply or the balanced ventilation. It's not coming through a duct. It's leaking through the building shell. There's studies that show that air coming in, the building shell and the insulation and whatnot actually acts like a MERV 9 filter, but it's not a it's not as desirable, let's say, air coming in as you would through a duct. So, you know, again, that's one of the criticisms. For our climate, however, using exhaust-only ventilation is more appropriate than, say, supply ventilation, because we're relying, again, on air leaking through that building shell. So in the winter, when you've got a big difference in temperature from outside to inside, you know, using cold, dry air as your makeup air, if you will, or your fresh air supply, can actually have a drying effect on the building components. So that's a benefit of exhaust only as well for our climate. Whereas with supply ventilation, you know, if we were using this in the north, which again we do and we have for years through that cold air scuttle connected to the cold air return, but in doing so, you know, there's a little added positive pressure in the home. And if you take warm, moist air that, let's say it's heated to 65 degrees and the relative humidity is 40%, and push that through the building shell to the exterior of the building to get rid of the stale air, you know, you can have that moisture when it hits a cold surface. If it's 0 degrees out in Grand Rapids and, you know, 40% relative humidity air is being pushed through the building shell, you know, we all know what's going to happen when it hits the OSB on the exterior of the building as it's exiting the building. It's going to you know, there's going to be condensation, and that can create building durability issues. In addition to that, your cost goes up a little bit here, because where before you were, you know, with the exhaust only approach, you're adding, you know, you had a bath fan there hopefully. Now you're just buying a better bath fan, maybe with a DC motor, you know, that runs very quietly and is very efficiently moving the air out of the home to meet your whole house requirement. With supply ventilation now, generally speaking in our climate, the approach with supply has been to interlock a damper that's running, that's connected to a tube that's running to the cold air return side of the furnace, and interlocking that with the furnace motor so that when the damper opens, the furnace motor kicks on and it's drawing air into the home, which of course then, you know, we have to consider the cost of the duct, the damper, and the controller on the furnace to open the damper when the blower motor kicks on. So there's those additional costs. And then having that blower motor on the furnace, of course, the long-term operating cost is higher as well, because the blower motor on the furnace is running as opposed to, you know, a bathroom fan or a fan in the kitchen that's exhausting maybe at 6 watts. You know, here, even if it's a DC motor fan, which I think is required in Michigan, if you're going to use this approach, you're required to upgrade to the DC motor on the furnace, and that's an additional cost. So we've got the furnace motor upgrade, we've got the damper, the controller. All of those things are additional upfront costs, and then we also have a long-term operating cost of the DC motor in the furnace running at a little higher wattage than it would be for an exhaust-only bath fan. One of the bonuses for this system is, as we're drawing air through that cold air scuttle into the cold air return and delivering it to the home, we're now going to filter that air. So we have an opportunity here to improve the air quality by running it across a good filter and removing the pollen and any contaminants that might be coming in on that fresh air that we're supplying to the home. So that's some of the benefits here. And another benefit might be that, you know, while you don't add a lot of negative pressure with a bath fan, you do add a little bit of negative pressure, and there may be, some people might be concerned about combustion appliances like a B-vent water heater that's, you know, going to rely on warm air rising to exhaust to the outside the combustion gases from the water heater. With supply ventilation, you're creating a little bit of positive pressure, and if there were any concern, it would it certainly wouldn't increase the opportunity for spillage there. With the exhaust-only approach, it does create a little negative pressure, not nearly as much as, like, say, a dryer or a kitchen range hood, but there is a little bit of negative pressure with the exhaust-only approach. So that's another benefit to the supply approach. And here's another diagram. This one shows, you know, the supply approach. You've got your bathroom fans there like we had before, but instead of using those as whole house ventilation, you'll see in the middle of the picture there, connected to the furnace, and running to the outside is a duct. And you know, what you can't see there is a damper and a controller that's turning the furnace motor on and coordinating the damper to open and allow the fresh air to come in. But that's the application there. Again, because we're going to be putting a little bit of pressure on the home with the supply-only approach, you know, we are going to ask, or, you know, we're going to be requiring that air leak out of the building somewhere, and generally it's going to be through the building shell or you know, under a doorway or whatever. So, you know, again, one of the cautions for this approach is that, you know, we don't want to create too much positive pressure and force that indoor air. It's stale, it needs to be exhausted, but it's also carrying some moisture with it. So pushing it through a building shell where it might come in contact with, or where it will come in contact with cold surfaces, especially in Michigan, Wisconsin, where we can get, you know, 0 and below during the wintertime, you know, we want to be cautious about how much, you know, pressure we're putting on the building to push that warm, moist air out through the building shell. So maybe not as ideal a approach for northern climates as it would be for the south. You know, we're in the south with positive pressure, we'd be most of the time pushing air-conditioned air out during the summertime through the building shell. And during the wintertime, there's not as big a delta T. You know, you're not going to get that minus 10 degrees in Florida where you've got those cold surfaces that moist air can be pushed out through. And oftentimes the air-conditioned air inside the building is drier than the outdoor air anyway. So this is probably a better approach for warmer climates than cold climates. Mike, would you agree?
Yes, I would agree. Yep.
All right. So let's move on to balanced. The balanced approach, we're going to, you know, again, the ideal situation here, we're doing some heat recovery. We're not creating positive or negative pressure, but there is a significant cost increase up front especially. And because you've got, you know, usually 2 motors in the HRV or ERV running, and oftentimes the install in our market is to interlock that with the furnace motor. Not only do we have the operating cost for the HRV, ERV, we have the operating cost of the furnace motor distributing that air throughout the building. And one of the big concerns long-term with HRVs and ERVs is homeowners struggle with maintenance. You know, we have a hard time getting them to change a furnace filter. We struggle even more to get them to open their HRV or ERV, you know, three, 4 times a year to clean that out. And I'm not bad-mouthing HRVs and ERVs. Panasonic makes ERVs, and I'd love to sell them because I do think it's the best ventilation system out there. But we have to look at how homeowners are going to interact with the equipment that we install, and that's been one of the struggles that we've had is homeowner maintenance of this equipment. So, but again, we don't have those concerns, those climate concerns, because we're not asking the building shell to leak air in or out, infiltration, exfiltration for the fresh air. We're bringing it in through a tube. We're running it across a heat exchanger, recovering some of the energy in the exhaust air and bringing that back into the building. And with an ERV, you know, not only are we recovering heat, we're recovering some moisture. So during the summertime, and we don't open our windows as much as we used to, you know, in the summertime when that warm, moist air is coming in, because an ERV will capture some moisture as well, it's going to, as it's exhausting the dry air-conditioned air, it's going to extract some of that moisture that's on the hot, humid air coming in and exhaust that instead of bringing it in to the building and loading up your AC unit. So there could be additional benefits to an ERV, although most of our climate or most of our market is HRVs. So here's a picture of that install, and you'll see that now we've got the furnace there, and we've got an additional piece of equipment to the right, that little small box with the stack on top of it. And it's running actually to the bathrooms, and this application, which I'm not crazy about, is also being used as your exhaust ventilation and for showers and whatnot, which, again, I'm not crazy about that approach, because if we install 150 CFM ERV or HRV and lose 10% of it to performance or to the ductwork, by the time you split it up in a bathroom or maybe a laundry room, the amount of air coming out of each of those picks is maybe not ideal to exhaust the moisture quickly enough to satisfy the homeowner. So I think I would rather see an install where we're doing spot ventilation fans to get rid of moisture, and then an ERV or an HRV to do the whole house portion of the ventilation requirements. All right. Where we install, what system we install matters. A Fargo, North Dakota install is going to have a different approach than a Miami, Florida install because of the temperature differences, because of the moisture levels. So we want to be thinking about where we're doing our install when we design our ventilation system, and we want to pick the best strategy for the climate that we're in. All right, let's just quickly review spot ventilation. Well, maybe I'll pause just for a second, Brett. If there's any questions, we could take a question.
Nope, not any questions, and we're coming close on our time, so why don't we keep going through, and then we'll get to the questions right at the end. So please, everybody, start putting them in as we're going. Okay.
So spot ventilation, which I would require, or I would recommend in any event, you know, getting the moisture from the shower and the odors from the kitchen out right at their source is the ideal situation. No matter what ventilation system you're using, I would recommend spot ventilation. Most of the codes will require that the bathroom fans be tested at an efficacy of 50 CFM, and if there's a range hood fan or a fan in the kitchen anywhere, it needs to be able to achieve 100 CFM intermittently. Quickly, in terms of sizing those bathroom fans, there's a couple of different ways to do it. We recommend 1 CFM per square foot for the bathroom, you know, in order to exhaust that moisture quickly enough. There's, you know, other ways too, like you see here, the calculation, V5 over 60. So the volume times 5, length, width, and height of the bathroom times 5, and you're going to buy that fan in CFM per minute, so you want to divide that by 60. All right, kitchen ventilation, you know, again, we want to make sure that it's minimum 100 CFM, and with any of these things, we want to make sure that they're quiet enough that people will actually use them. So that's a big consideration as well. Again, I don't want to spend a lot of time on how to calculate the whole house ventilation requirement, but I did want to touch on it just so you have a little background. You know, with the ASHRAE calculation, you would use the number of bedrooms plus 1. This formula here that you see, number of bedrooms plus 1, because we're going to assume 2 occupants in the master bedroom, times 7.5 CFM per person, if you will. And then we also have to have a square footage calculation for the home. And you'll see the difference there on the left between the 2010 calculation and the ASHRAE 2013 calculation. The only difference really is the calculation for the square footage going from 1% to a 3% calculation. And then on the bottom there, you can see the difference in the code, or the difference in the requirement of ventilation for whole house continuous using those 2 different ones. Now, Michigan has adopted the ASHRAE 2010 chart, essentially. So here's the 2013 chart, number of bedrooms, square footage of the home. So if you had a 4-bedroom, 2,600 square foot home, and you were using this chart, we would go right over to 145 CFM. With the 2010 version, we're going to be at 75 CFM. And what you'll notice is, if you look at this chart here, and now this next picture, this next slide, is right out of your Michigan ventilation code. You'll see that they're an exact match. So your Michigan ventilation code is based on the ASHRAE code, was my point in bringing all of that up. All right, so let's talk a little bit about installation techniques. We talked a little bit about this earlier in the presentation, but essentially, and again, I've been swimming through the fiberglass with many different installers over the years, whether it be HVAC contractors or some of the tribal housing authorities or weatherization agencies or whatever. And, kind of what I came to in the end was something to help them remember what I wanted to tell them about their ductwork. Again, you can buy the best equipment in the world, but if you don't duct it right, or you don't put a good termination on the end, you're going to choke that down. So, and this might sound a little corny, but hang with me. I used to tell them to kiss their ductwork, and that, again, might sound a little corny, but keep it short, keep it straight, and keep it smooth. And if you just remember those things, it's going to help the performance of the fans. And even if you're using flex duct, I think the manufacturers recommend that you stretch that flex duct to 5 pounds of pressure so that it smooths out the inside of that flex duct and reduces the static pressure, so you don't get cavitation when that fan is pushing air through that duct. So again, if you keep it short, smooth, and straight, and then put a good termination on the end of it that doesn't have a lot of resistance, you're going to certainly improve the performance of the equipment. And where you terminate is important too. I like soffit terminations because it's often the shortest distance to the outside, straight down between the truss, over the top plate, and out the soffit is the shortest distance to the outside. I like that approach, but we got to make sure that we're not putting the termination near a vented soffit panel, of course, where it's just going to suck that warm, moist air back up into the attic. So we want to make sure that the termination is installed in a unvented soffit panel, and that there's an unvented soffit panel to both sides of the termination, so that the moist air can work its way out. And we want to point that termination so that it's blowing out from underneath the soffit as well. If you've got HRVs and ERVs, you want to be careful where you put those intakes, because if it's Sunday afternoon and the Detroit Lions are playing the Green Bay Packers, and you see next to that green, I'm not sure what the green thing is in that top picture, but next to that, behind the grill, is an intake for an HRV or an ERV. Well, if you're grilling brats and sauerkraut on Sunday afternoon, and that intake is sucking the air into the building, your whole house is going to smell like brats and sauerkraut. That may not be a bad thing, but you just want to be conscious of where you're putting it. You don't want to build a dog coop around your intake for your HRV or ERV, certainly. And we also want to make sure that they're spaced far enough apart. Like in the bottom picture there, you'll see on the left there's 2 exhausts, and on the far right a fixed grilled intake. We want to make sure that we're not getting cross-contamination. And we want to make sure that we're not, doing stuff like this. If you watch ESPN, I like it. I like the program where they're like, "Come on, man." And that's what you should be thinking when you see installs like this in the homes that you build. The shorter it is, the straighter it is, the smoother it is. If you see stuff like this, somebody needs to correct it. Somebody needs to ensure that that ventilation equipment is being installed properly, and that we're not, hurting it by doing installs like this. All right, so that's the end of my presentation. By now, hopefully we understand the necessity for ventilation, and we understand the differences between whole house intermittent and spot ventilation, as well as exhaust supply and balance ventilation. Proper sizing, you know, you guys just use your charts for that. That's the easiest way. And then we talked a little bit about sizing the bathroom fans, and then how to install it properly. So that's it. If anybody has any questions, yeah.
Jeff, I'd like you to touch on the fan efficacy requirements of MUEC 2015 for ventilation fans, and which would include bathrooms, kitchens, inline fans, and ERV, HRVs.
Well, Mike, I'm going to actually have to kick that back to you because I'm not as familiar with the efficacy requirements, unless maybe when you start talking about it, I'll get what you're talking about. But maybe I'll kick that back to you, Mike, on that one.
All right, that's fine. The code requires that you, for fan efficacy, that you have 2.8 CFM of flow per watt, and that is on bathrooms and kitchens and ERVs and HRVs, and 1.4 CFM per watt on inline ventilation. And then one thing you did touch on is the integrated system where you're using the mechanical system, HVAC system, to provide ventilation. That the option there, or the requirement there, is for that to be an ECM motor. One of the things that we're finding out now that we've been under this code for the last 10 months is a lot of manufacturers don't put fan efficacies in their literature. So we know that we've got charts from Panasonic, which are very helpful, that show that the green series of fans certainly meet the efficacy in bathrooms. But the ERVs are a different story. I've only found one ERV that actually had the fan efficacy, and it happened to be 4 CFM per watt listed, but a lot of them don't have them. So it's really, really important that we make sure that we do meet those efficacies, because we are required when we're doing the inspections to verify that. So make sure that the builders make sure that they have the literature to provide to your inspectors, showing what that efficacy is, so that you don't run into a problem at the end of the cycle when they're evaluating your ventilation fans.
Okay, can you go over quick again, what was the requirements for bath fans, inline fans, and ERV? What were those numbers again?
There's two numbers. There's 2.8 CFM per watt, and that would be for mechanical whole house ventilation, or for your makeup air ventilation system. So you're looking at bathrooms, fans, kitchen fans, ERVs and HRVs fall into that category. If you're using a push-pull fan, that's just and that's integrated into the system, but it's integrated into the duct system, but it's its own fan damper arrangements that are providing that. That's 1.4 CFM per watt. That's an inline system. If you have an integrated system like you had shown in your example, where it's the furnace fan that's actually creating the pull on the damper, which pulls fresh air into that 4-inch or 6-inch makeup tube, that has to be an ECM motor.
Okay. How is that being measured, Mike? I mean, I understand with a bathroom fan or a kitchen range hood, you can put a barometer, you know, over the bathroom fan or whatever and measure the airflow that way. How are they verifying the fresh air supply system, if you will, that's sucking air into the cold air return? How are they verifying that they're meeting their code requirement with that? Because when we've tested that system in Wisconsin, we've noticed that the CFM actually being drawn in is very, very minimal. There
isn't any. First of all, from a code perspective, there isn't any not verification of those flows. What the code requires is that the fan efficacy meet these requirements that I've just given you. But in touching on what you've just asked about, many of the above grade programs mandate testing of flows for bathrooms, kitchens, and mechanical ventilation systems. And those those above grade programs are LEED for Homes under LEED V4, Energy Star version 3, to name 2 off the top, that actually require the airflow measurement, which is why I'm glad that you spent so much time on covering the install of these fans in the ductwork, because there's a lot of failures on meeting the flow requirements when ducts get pinched, or there's multiple bends in them, or excessive lengths, or any type of thing that doesn't that impedes the flow of the air. So it isn't mandatory now. It is going to be recommended in the future, and we're already seeing it in above grade programs that testing is mandatory. So we have flow hoods that we can actually test now when somebody does a LEED for Homes program, and they're going for EQ 5.1, the credit, or 5.2, which is actually measuring the flows, 5.3, 6.3, and 4.3. We have flow hoods that we can check those, but it's been our experience that they are either over ventilating or under ventilating because they're not paying enough attention to the install.
So I want to go back to my question, Mike. How are they, in those above ground programs that you talked about, LEED, Energy Star, how are they testing if they're using the supply system? I've never seen anyone test that system. How do they test that system? I'd like to know so that I can do the testing myself.
Yeah, we would do that from the exterior of the home with the flow hood. But I will tell you that typically what is happening is we're being provided with calculations based on optimal performance. So if you've got a 25 Pascal pressure on the duct system, and that has a 4-inch fresh air intake, that's typically somewhere between 35 and 40 CFM of fresh air being supplied. But that doesn't take into consideration the install, that's just under optimal performance, and it's about 67 CFM under a 6-inch duct. But that's all theory. It's not in real world practice. So when we go to verify those flows for these above grade programs, we'll use a flow hood or some pressure pan system that we can measure those with, and we'll find that they're woefully inadequate for the ventilation requirements or fresh air requirements of that system.
Yeah, that's been our results as well. We've actually taken flow stations, put them in line, and I think the top test was like 37 CFM coming in through a 6-inch scuttle, and that was pretty close to the furnace, where the negative pressure in the cold air return is going to be pretty high, or higher than it would be further down the line, because as you mentioned, where they install it, how they install it has just a huge impact as well.
Yeah, I've been doing evaluations on residential construction for over 35 years. And most of it, the first 20 years, was probably, well, it was all occupied structures that have been occupied for a very long time, and have seen the amount of indoor air quality problems, comfort problems, sick building syndrome issues that are the direct result of improperly imbalanced ventilation systems that have been installed. And one of the things that we hadn't talked about, the buildings have definitely been getting tighter, and that started in 1973 or so, about the time of the oil embargo, where we really started paying attention to air leakage in the homes. So we've tightened them up. But over that period of time, we've also introduced a tremendous amount of chemicals, a toxic soup, if you will, into our homes, from cleaning supplies and fabrics and fabric protectors and all of this type of stuff, paints and varnishes and glues and solvents, things that we know independently we know what their health risks are, but we've never done any evaluations of what the overall health risk is of this chemical soup. And so mechanical balanced ventilation systems are extremely important, so that we're not pulling, I look at the overall life cycle cost of ventilation as being the initial upfront cost, and then the operating cost, and then the energy cost of reconditioning air that's being taken in against the air that's being lost, and then the health costs that are all added onto that. So this is one of the most critical aspects of the new code. In 2018, and we don't really have time for that slide, Brett, but in 2018, the IECC recommendation is that all homes, all new construction has mechanical ventilation that's of ERV or HRV type. And so we are addressing these, but we're way behind the curve on the learning curve. So we're heading in the right direction. These are great options in the state of Michigan, and we lag the industry even beyond the codes do, because we're kind of stuck at 2009. But we're much farther ahead than we were when we were operating in a 1982 code for the last, before 2009 came around, a modified version. So we're heading in the right direction.
Yeah, that's definitely one of the things that I, was happy to see when Michigan did adopt the code, was that they didn't just take a little leap forward. They were behind on this stuff quite a ways, and they actually took a big leap forward, jumping up to the 2010, ASHRAE code essentially. Let me ask you another quick question, Mike. In terms of the efficacy, 2.8 CFM watt or per watt or whatever, would you say that an Energy Star logoed product would be a good indicator of that efficacy?
It might be. I couldn't say for sure, because I don't know what the requirements are to be Energy Star. It used to be that there had to be a proven energy performance, but we've found quite often a lot of Energy Star products didn't meet the actual performance that they were looking for. So we're going to be looking for actual charts, and I have seen them, the charts on the Whisper Green series, and most of your bath fans have an efficacy of somewhere around 6 or higher CFM, so certainly qualifies. And like I said, I was looking at HRVs and ERVs because we've had some houses that have had those installed and have found that the efficacy on some manufacturers are not listed anywhere, and I've only found one so far that had an efficacy of 4. So we're going to be looking for that stuff, so make sure that it's on your literature, I guess. And you guys are, Panasonic is already ahead of that curve. So I'm speaking to the people that don't necessarily use that product to make sure that they have a listing, because if you're going a performance pathway and a guy like me is going to be involved, I have to see that verification on your paperwork, or have to be able to find it somewhere. If you're doing the prescriptive, then you need to provide that information to your local code official that's going to come in and do the inspection, because the efficacy is a mandatory requirement.
I just want to do.
Well, I want to give everybody, it's a little bit over 10 now. I definitely want to give all of our guests here a chance to ask some questions if we haven't had a chance to cover everything. But we got a lot of great conversation here, Jeff. I know you were saying a couple more things, so feel free to continue with your line of thought there. But I wanted to make sure everybody knew they could certainly chime in and ask some questions.
Yeah, great. Yeah, I'd love to answer some questions. That'd be great. While we wait for those questions to come in, Brett, you kind of baited me on this a little bit before, but then I wanted to speed things up a little bit. So when we talked about balanced ventilation, I didn't talk about what we would call maybe a hybrid system that Panasonic offers. Now that our presentation's over, I'll go into a little bit more of a sales pitch here, but not too hard. We've got a product at Panasonic called the Select Cycler, and that product kind of marries up exhaust and supply to create a more cost-effective balanced solution, in that while it's not going to do any heat recovery, it's going to use that cold air supply scuttle with the damper and the furnace motor running, and at the same time have the bathroom fan running, or a fan in the home running, exhausting air at the same time. So we're just adding a controller like you would have for, that's the same controller you would have if you were supplying, using the supply-only system, but now we're tying the bath fan to it with a wall switch that tracks how many minutes per hour it runs, and actually is more balanced than, say, just an exhaust or a supply approach would be, because our blower motor on the furnace is sucking air into the building, and we have a bath fan or a kitchen fan running and exhausting air from the building at the same time. So it's balanced in that sense. It's not balanced like an HRV or ERV, and it's not doing heat recovery, but for a much lower cost, you have what we call a hybrid balanced system there. So that's called our Select Cycler, and you can check that out on our website, Panasonic/vent fans. And then as you see the slide that's on the screen now, I'll also mention that if you are a member of a local HBA, you can go to the HBA website under manufacturer rebate programs, and you'll see Panasonic there as the only ventilation company that's offering a rebate if you use our fans. You have to track those and then report them, in, of course, but you certainly would qualify for a rebate through your local HBA. Any questions come up there, Brett? Are you there, Brett?
I'm looking at the question box.
I don't see any questions coming in here as of now, but I do want to give everybody the opportunity to ask any wrap-up questions to Mike, to Jeff, anything we talked about. All of this will be recorded and accessible for free on our YouTube channel, on our website. It'll be on the USGBC channel. As we're waiting for some more questions to come in, I wanted to wrap up with one thing we've been piloting in here in-house, and that is, let's kind of roll through some of this. We're working with the Department of Energy utilizing their new Home Energy Score tool. It is a tool that's primarily made to make an impact on existing homes, but we have found a value in it on new home construction, actually, believe it or not. You can use it for new homes. And one of the benefits of this tool, any rater or assessor or BPI contractor that you're working with to already do the required mandatory blower door testing for your house can actually come to our website and get training on this. It's all done online through a simulation and some open book, open note, no cost other than their time. Take a whole weekend and knock it out to become an assessor. But one of the benefits of this tool is that it gets you everything that the code officials are going to need in a nice, well put together report that could also be given to a homeowner to show them sort of where their home is scoring in relation to the rest of the homes in the community and how much energy they're saving or using depending on the construction build type. And so it gives out all sorts of facts, all the things that the code inspectors need, gives out energy use predictions per year and with relative accuracy we've been finding. So again, homeowners can understand what their miles per gallon costs are going to be. And again, here's some examples of attic foundation, walls, windows, skylights, and you name it. So those are all facts that will be given out. Again, that can be given to the code inspector, given to the homeowner. And so we've been piloting this out, and it has been getting accepted as a means to meet the code. It's again, it's above and beyond, but it generates the report that everybody essentially needs. So you can check that out. If you have assessors, they can reach out to us. We have a free 1-hour webinar on our YouTube channel on how to utilize this tool. It does capture ventilation needs as well. And again, gives out a nice little score and a packet that the homeowner can use that is also getting tied into financing. And one of the other benefits that, again, you can work with us and the assessors on the front end to design the house with the tool and the assessment in mind to drive that score down and get a good return on investment before you even build the house. And so you can do the preliminary modeling with your assessor. You can do it with us here in the office. We'd love to sit down and go over it with you for a pilot. And then you can implement those in the field, and then the rater will come in and assess it during the code inspection testing. So that's all we have here today. So I didn't see any other questions. So we're going to go ahead and wrap up. I want to thank Mike Holcomb, our founder and former president, owner of the Home Inspector General, for leading us through these past 3 sessions. Jeff Klanowski from Panasonic for taking us through the ventilation. please reach out to any of them if you have any further questions or something come up, or send this on to any of your contacts or builders that you work with, so you can help share the knowledge. So thanks again, everybody. Take care.
Thanks, Brett.